This might come in useful. Okay, so there are the learning targets for today. As I just mentioned, those 3 learning targets. I got to warn you ahead of time, this is a lot of content and it can be kind of hard to figure out at first and can be kind of confusing. So if you are kind of confused by the end of today, do not worry. Just know that what's the key? Can you all say it with me? Spaced practice, right? We're going to keep working at it, keep looking at different scenarios, different problems to help you understand these concepts. And we're also going to use some very important analogies. The other thing I want to say is if you aren't keeping up with the async work, for example, yesterday's async work was really important. I said that in the remind message. If for some reason you didn't get it done, just know that it'd be really to your benefit to get that done as soon as possible because that'll help you understand as well. A quick space practice exercise. Like I said, your async task actually from yesterday, not last week, was to take notes on electric field basics. So from memory, try to recall the following. Don't look at the notes, just try to answer these 3 questions, speaking out loud to yourself for the next 20 seconds. 1, what is an electric field? Describe it in general. 2, what do the field lines represent? And 3, I can't number these things. What is the general equation for electric field? Ready, set, go. And time is up. Okay, if you struggle with answering any of these questions, that's great because that means you are gonna be learning, right? You learn more in the struggles. So go to look at your notes and refresh your memory. You can take another 20 seconds to do that. While you're doing that, I'm just gonna write some quick sort of responses here. But again, I would not take my responses as being the be all end all. You should definitely go back and refresh your memory. Okay. I'm gonna kind of go over these things quickly, but again, this is not notes that I think you should be taking. Hopefully this is stuff that you already have in your notes. So my quick answer to what is an electric field is an electric field is a distortion in space caused by a source charge. The field lines, what do they represent? They represent a lot of things, but the simplest thing I would say is the direction in which a positive charge will feel an electric force. And the most general equation for electric field is electric field equals force per unit charge. Okay. Oh, I forgot. I'll give you that to you in a second here. Okay, please go to your notes, your electric field notes, if you're not already there, because I want to add a little bit to them. If you didn't do that assignment yet, then consider this your start to doing those notes. So I'll give you 30 seconds here to set up or go find your electric field notes. There's no need to draw this elaborate drawing. You might want to just simplify it a bit. And just a heads up, because this is so such a complex topic in many ways, I'm going to put into the chat a copy of the notes I'm about to go through. So if you followed it behind or whatever the case may be, those are the notes that I'm going to start going through in a couple slides. Okay. Okay. So one of the things I want to make sure we understand about electric fields is the following. Notice this electric field over here on the left. This is an electric dipole field. And the key idea I want you to understand here is if a field line is curved like that, then let's say I have a positive charge located right here. The question is, what direction will it feel a force at that point? Well, it feels a force in a direction that's tangent to the field at that point, okay? So in this case, man, this thing is acting weird. The electric force would be right here because I'm trying to draw a straight line tangent to that. Similarly, over here, if the charge was over here, in which direction would a positive charge feel a force? It would feel a force in this direction, like so. Okay, so that's one of the first key ideas. The direction of the electric force on a positive charge is in the direction of a line that's tangent to the field line. Okay, if the field line is straight at a certain point, then obviously it's just going to be straight and there's no tangent to speak of. Second thing I want to talk about is, let's take a look at this middle scenario here. Notice I have a source charge, a point charge, a positive point charge, and that's the electric field that's created by the positive point charge. And notice I have that blue dot and that red dot. And the question is, I'm going to draw a box here. I'm going to draw a box that's like yay big. I'm going to draw a similar size box over here. Okay, I tried to make those about the same size. And the question is, what are field lines drawing good for? And here's one thing I want to make sure, this is the key point that I want to make sure you understand, is the density of the field lines. The field lines give you a qualitative sense of how strong or weak an electric field is, electric field. And how does it give you that? It's because you look at the density of the field line. So for example, in this drawing, notice I have one field line that goes through this box. Same size box for the red dot has 1, 2, 3, 4 field lines going through it. So one would have to conclude that the field strength, the strength of the electric field, is much greater at the red dot than the blue dot because the field lines are closer together. Okay, so where the field lines are closer together, the electric field strength is greater. And that's something you often heard talked about as field line density. Similarly, in this third scenario, I have these two plates, and assume these plates are really long, and the distance between them is really small compared to their length. Okay, and if I apply the same idea as last time, then that we were just talking about, then when I draw a similar size box, and notice in this case, at the green dot and the orange dot, I get the same number of field lines going through it. Okay, so where the field lines density is constant, then that means the electric field is constant. So for example, if I knew that the field strength was 5 newtons per coulomb at the green dot, then it would also be 5 newtons per coulomb at the orange dot. And that might mean, if I go back to this earlier problem, just to kind of compare this might be 1 Newton per coulomb, and this guy here might be 10 newtons per coulomb, okay? Again, field lines in and of themselves do not give you numbers, do not give you quantitative numbers, but they do give you a qualitative sense for what's going on. Final thing I want to make sure you understand is field lines cannot cross. Okay, notice none of these field lines cross. And you can imagine a scenario where they did, it would be kind of odd, because if I had a field line like this, another field line like this, then right here, which direction is this point charge going to feel basically the net electric force from the source charge? It's ambiguous, right? And that can't be. You can only feel a net force in one direction, a net electric force at least in one direction. So field lines cannot cross. This does not work. Okay. All right, so I want to walk through an electric field sample problem because you're going to have to apply one of these in your breakout rooms. So notice what I have here is I have 3 scenarios, and they're independent of each other. They're far enough away from each other in space that they don't impact each other. And in each case, I have 2 source charges. In A, I have these 2 positive source charges. In B, I have 2 negative ones, and C, etc. And I have a blue dot. And the question is, I want to rank these 3 scenarios in terms of the size of the net electric field at that dot. And now remember, electric fields are vectors. So given that they're vectors, you can basically find out the field contribution from each source charge and then add the vectors together to get the net result. And let's walk through and see how that works. So the other thing you should have gotten from the async task yesterday was this field equation. For a point charge, the electric field strength is equal to KQ over R squared. So that's for a point charge. Okay, and so let's think about this. If I'm at the blue dot, what does the electric field vector look like from this positive charge number 1? I'm going to call this 1, I'm going to call this 2. So remember, that's the blue dot is going to, the field is going to go in the direction that a positive charge would feel a force. So a positive charge would feel a force away, and I'm just going to make this an arbitrary length, but then I'm going to try and keep it constant. So this is the field contribution from source charge 1. What's the field contribution from source charge 2? Well, it's going to, at this point, again, show a vector that's going to be the opposite direction, because a positive charge would feel a force in that direction. So this would be E2. Now the net is going to be the sum of those two. Right? And in this case, they're going to cancel, right? If I do a vector sum of this, it's going to cancel. My computer is malfunctioning, but that's okay. So E net equals 0, right? If I do tip to tail, adding them like I did there, right? It's going to be 0. So we know in scenario A, the net electric force at the blue dot is 0. What happens with B? With B, notice I'm going to call this 1, and I'm going to call this 2. From source charge 1, I get a net electric force that would go down, electric field, I should say. And then from source charge 2, I also get a field line vector pointing down towards it. But notice it's further away. And since it's further away, and then I'm squaring it per this equation, it's going to be a smaller vector. It's going to be like 1/4 the size of E1. So I might draw something like this for E2. And so when I add these together, this is really touchy. Sorry about this, folks. When I add these together, I get a net electric field that looks something like this, okay? Again, I'm adding them tip to tail. So it's a bigger vector than either one individually, and it's down. All right, and finally, the third scenario, the electric field components from each. So I'm going to call this 1, and I'm going to call this 2. So from 1, let's see, that's going to feel a force up, but it's going to be small because it's further away. So it's going to be a small vector like this. So that would be E1. 2's vector is going to be in the downward direction and bigger than E1 was. So that might look something like this. So the net, when I add 1 and 2 together, is going to get me a vector that's pretty small. It might look something like that. Okay, so now I know enough to rank these scenarios. And so how I would have to rank them is right just from the size, the magnitude, the strength of the E field. Well, A is clearly the lowest, right? Because it's 0. And B is clearly the biggest because those two vectors add together, and C is in the middle because the two vectors oppose each other, and they create a net vector that is somewhere between 0 and the size of one of them. Okay. So this is an example of how you would treat a problem like this, where you're given multiple source charges and told to rank different scenarios. And the key idea here, one of the key ideas here is that electric fields are vectors, right? So you can add them vectorially. Okay. All right, so now it's time to kind of start a new set of focus notes. So go ahead and set up a new set of focus notes, electric potential energy and electric potential. And there are two essential questions there that I'll give you about a minute here to copy them down. And by the way, again, you can always do this digitally if you want with a digital template, or you can do it with hand, pencil, and paper. And while you're doing that, I just wanted to tell you that on Sunday I went to the Portland Timbers game, and it was a good game, even though the Timbers lost. But I didn't realize they were letting in electrons into Providence Park. You know, fans that are electrons, and I had an electron sitting not too far from me, just basically being quite loud during the game, which was fun because they were a Timbers fan. But did you know what is an electron's favorite chant at a sporting event? Charge!
Ha 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 ha.
Ha ha ha.
Thank you. Thank you. I think that was Hudson and Callan with the live laughter. And I see Sophie and Braden and Clara and Palace and Jason. Thank you very much. Okay, so here we go. Let's go on this journey of electric potential energy, electric potential, and a lot of other things. Yes, Claire, they must like jousting. All right, so I just want you to mainly listen. Again, first and foremost, most important thing always is to listen, but especially in the next few slides, I would say. I'm going to try and build up these new concepts by using an analogy. And so here's the analogy I want to use. So let's say I have my phone here, and or you can see this, there's a book there. And if I basically take my phone, you can see it there in the view, and I lift it just about, 10 centimeters, I'm exerting a force causing it to travel through a distance, right? Force, travel through a distance. That's one way of conceptualizing work. The other way that someone might say, hey, Mr. Bob, you're actually raising the gravitational potential energy of the phone by taking it from this lower position in this gravitational field to this higher position. And all those statements are true. Okay? So I've changed the gravitational potential energy of this object by exerting a force and causing it to move through a distance. Okay, next scenario, I have a coiled spring, okay, and this coiled spring is at its natural length to start out with, but then I push it in with my hand, right, and I push it in so it is compressed. What would we have to say is happening to the elastic potential energy of the spring? Well, we'd have to say the elastic potential energy is being increased, right, because I'm displacing that spring from its natural length. At the same time, we could also say I exerted a force on that spring to make it move through a distance. Okay, so notice what's happened here in both of these scenarios. I've done work on the system somehow. I've done work on the book or my phone. I've done work on the spring, exerted a force through a distance, and that's correlated to a change in potential energy. So the work done is equal to the change in potential energy of these objects. Okay. So let's now look at this third scenario here. This third scenario, notice what I have here. I have source charges here on the right, and there's a positive charge on the left. And I take my hand on that positive charge and I push it, force that positive charge closer to the source charge, which is also positive, which we know it doesn't want to do naturally. Okay, so notice what I've done. I exerted a force on that positive charge, moved it through a distance. So wouldn't it make sense that in just like the other scenarios, somehow the potential energy of the system of that positive charge has increased? Shake your head, yes. And that brings up a concept that we call electric potential energy, okay? And electric potential energy is exactly that. It's this idea that charges, particles with net charge, can have a certain type of energy, a certain type of potential energy based on their location in an electric field. Just like the book has a certain amount of potential energy because of its location in a gravitational field. Okay, so electric potential energy can also be thought of as the amount of work that must be done to assemble a set of charged particles. Meaning, if I have these particles start off very far apart from each other, then I have to do a certain amount of work. I have to put in a certain amount of energy to get these positive charges to be closer to each other. Similarly, if I had a book at the bottom of a hill or something, I'd have to do a certain amount of work to get that book partially up the hill. Okay. And so you could think of a change in electric potential energy as the amount of work that has to be done to get that charged particle to move between 2 points in an electric field. Just like I could say the change in potential energy, gravitational potential energy, for me is how much work I have to do to lift my phone between the 2 points in the gravitational field. Okay, now this next slide is has a lot of information, but we'll walk through it slowly. So there are these terms, and I'm going to be upfront again and say they can be confusing. There's something called potential difference. There's also we could think of it as change in electric potential energy per unit charge. Let me explain with the scenario here. All right, here we go. Let's say I have a source charge, big ball of source charge, Q. It's positive. And let's say I have another charge, small lowercase q, and it's originally at point A, and it's going to move to point B. Okay, it moved a little past point B, but just assume it stopped at point B. So we have this concept that we call electric potential difference. And remember, difference, that triangle is delta, and the capital V is commonly used for potential, electric potential. Or capital V is actually commonly used for potential, and then the lowercase e signifies it as, being electric. And so the definition here is that the electric potential difference between 2 points is the amount of work done per unit charge in moving a point charge from A to B. Okay, again, it's the amount of work per unit charge to move Q from A to B. I hope you got the sound effects there. You can also think of it, and I would encourage you to think of it as the change in electric potential energy per unit charge. So these are the equations. Triangle VE, that's electric potential difference, equals work done per unit charge, W over Q, or it's the change in electric potential energy per unit charge, delta EP over Q. It's important to note that the units on here are work is in, or energy is in joules, if you recall. Charge, we learned recently, is the SI unit is coulomb, so it's a joule per coulomb, okay? But we actually use a more common term for this. More commonly in physics and in everyday language, we use something called a volt. 1 joule per coulomb is known as 1 volt. Okay, hopefully you're starting to make a connection here, or maybe even if it's a fuzzy connection, I'll take it, between everyday language and what's actually going on. And when we get to circuits, we're often going to use the term voltage, okay? And that's what you hear in common day language. A 9-volt battery means that between the top terminal, to basically get a charge from the bottom terminal to the top terminal of that battery, or the 2 terminals if they're side by side, it requires 9 joules of work for every coulomb of charge you want to move between those terminals. Or as the charge naturally flows through a circuit from one terminal to another, it's able to do 9 joules of work for every coulomb of charge flowing through. Okay, those are 2 ways of thinking about it. All right, a quick joke. What did Cinderella say when her mail order photos did not arrive? Someday my prince will come.
Ha 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 ha.
All right, thank you. Thank you. I appreciate the positive response in the chat. I don't think this one is as good as the other one, but anyway. Okay, let's talk something about, let's just make sure we understand zero reference point and something called electric potential. So if you recall originally on your equation sheet, if you look at it right now, there's this equation that we learned back earlier this year, that the change in gravitational potential energy equals the mass of an object times the acceleration due to gravity times the change in height. But if you recall also, we often set, in these problems, we often set a zero reference level. So for example, usually the surface of the Earth was, we said EP equals 0 here, or H equals 0. Either way, it's the same thing, okay? So recall that for gravitational potential energy, we often established a commonly understood 0 point. Most common one was the surface of the Earth. And so when we do that, then we don't have to talk about the change in gravitational potential energy. We can just talk about the amount of gravitational potential energy an object has, as long as we all have the understanding that we know where 0 is. Similar idea with electric potential energy. There's a commonly understood 0 point. So you're going to often see problems, textbooks, websites, everyone talk about just the electric potential, right? And the electric potential equals the potential energy per unit charge. Okay, so like a 9-volt battery has, that positive terminal of the 9-volt battery has 9 volts of electric potential, because everyone understands the negative terminal is referenced to be 0 volts. Okay, so electric potential equals potential energy divided by charge. All right, here we go. This is a really good problem, and I want you to watch what's going on here. How are electric potential energy and electric potential related? Because these two terms commonly confused with each other. So notice I have a scenario here where I have some point charge, source charge over here, and I have a point charge that starts over here at point A, and it's the point charge has 2 coulombs of charge. And I tell you that the electric potential energy of the 2 coulomb charge at that spot, is 6 joules. Okay, so the first question is, I tell you that it takes 4 joules of work to move the charge from A to B. So what is the change in potential energy when I move the charge from A to B? Well, remember, the change in potential energy is equal to the work done, right? So that was one of the definitions we just talked about. So that's just going to be equal to 4 joules. All right. So then the next question we could ask is, what is the potential energy at point B? Well, to know that, we have to know what the potential energy at A was and what the change was. And we know that at A, it was, it was 6 joules, and we just learned that the change is 4 joules. So the total is going to be 10 joules. Okay. But if I ask you the question, then what is the electric potential at points A and B? Electric potential, what is that? Well, the electric potential, if you remember, is the electric potential energy divided by the charge. Okay, so if I'm going to figure out the electric potential at point A, I got to figure out what is the potential energy at A and divide it by the charge. The electric potential energy at A was 6 joules. The charge is 2 coulombs. So that means it's 3 joules per coulomb, or 3 volts. So at A, the electric potential is 3 volts. What is it at B? Let's see, at B, the electric potential at B, can't touch the screen without it going haywire. Yep, makes it really hard. It's the curse of being a lefty. Electric potential at B equals what? The electric potential energy at B divided by Q. And so that would be 10 joules divided by 2 coulombs, or 5 joules per coulomb, which equals 5 volts. Okay. So notice if I ask you what is the electric potential energy at a spot, you're going to give me an answer in joules. If I ask you what's the electric potential at a spot, you're going to give me an answer that is in joules per coulomb or volts. I often see students confuse the two, and it's understandable why you confuse them, but this is why I'm working through this problem with you. And in fact, this is so important that I'm about to change the slide here. And we did that. Yep. Oh, wait, hold on. We did that. What's going on here? Okay, there it is. Sample problem. Try one for yourself. So I'm going to pause here for 2 minutes. And I want you to take the next 2 minutes to work on this problem and see what you can come up with. Please begin. And then we'll go over it together. Okay, so there you can see the my answers. And just very quickly, the work done is equal to the change in potential energy, which is 9 joules. Okay, so the potential energy at charge of the charge at spot B is 21 joules, and you get 4 volts and 7 volts for the electric potentials at A and B respectively. And then the last question was kind of one more that I threw in there. The potential difference, just as the name implies, would be the difference between the electric potential at A and B. So the electric potential difference would be 3 volts, 7 minus 4. All right. Are we done? I think we might be done with the notes. I hope so. Yes. So equation sheet. The equation sheet that you have now that is also on the Canvas homepage looks like this. And I want to kind of point out these are the equations we have been talking about in the last couple of weeks, including today. These are the ones you're going to have to use in the breakout room here in a couple minutes. Okay. So notice we have Coulomb's law and we have the electric field equations and we have the potential equations now.